All right, let's pick off where we left off on the slideshow. All right. So last slide, we went through my step-by-step process of finding a function's extrema. And here is an error of caution that I already outlined in the Jamboard, but I'll read through this slide again to kind of emphasize the point that I was making. We looked at the graph of 1 over x squared. At x equals 0, the derivative is undefined, and the derivative around it changes signs. It seems to pass our test for local maxima or minima, but there is no maximum there. Additionally, can a maximum or minimum occur at a hole? Remember, a hole is just another place where a function is defined. Sorry. A hole is another place where the function is undefined. No, it can't. Because remember, it's the same reason for why if we had endpoints that were, or if we had an interval that was open, so the endpoints weren't included in it, there will be no maximum or minimum. If there's a hole somewhere, there's no definitive maximum value, even if it looks like there should be there.
Yeah.
Does that sound intuitive?
Definitely.
Okay, cool. What does this tell us? Well, if the denominator of the original function is 0, there is either a hole or a vertical asymptote there. Would you agree with that?
Yeah.
Right. Thus, the x value that makes the denominator of the original function 0 will not have an extrema there, even if it passes the derivative test. Cool with that?
Yep.
Okay. This is vital because sometimes these points can pass our first derivative test and be sneaky, like 1 over x squared. But to check our final answers, we have to make sure that the x value will not make our original function undefined. It is okay if just the derivative is undefined, but the function itself cannot be undefined. All right?
Yeah.
So I put cube root of x as an example because even though there's no maxima or minima at x equals 0, the derivative is here is undefined, but the function itself is defined here. All right. So if we were to come across a function where it would pass our derivative test and the derivative is undefined and it passes our first derivative test, all right, that's fine as long as the original function is defined there.
Yeah.
All right. So it's fine for the derivative to be undefined because yet again, that's where we have a critical point.
Yeah.
We just can't have the first original function be undefined.
Yeah.
Cool. Awesome. Any questions?
All good.
Cool. Wrong way. All right. Breaking a function in intervals. All right. The derivative of a function can only change signs at critical points. All right.
Yep.
This means that critical points can help us break the function into intervals where the derivative is entirely positive or negative. And as an example, I said, let us look at the graph of y equals x cubed minus 5x. We could do that, but I might just do it very quickly. All right. So the idea of maxima or minima, right, can help us break the function into sections where the derivative is purely positive or purely negative. All right.
Yeah.
Here's what the graph of y equals x cubed minus 5x looks like, generally speaking. All right. And you'll notice that here's a critical point and here's a critical point.
Yeah.
Because the derivative is 0.
Yep.
And they're the only critical points. There's no other point where the derivative is 0 or undefined.
Yes.
And you'll notice that these points are maxima or minima, coincidentally. And the derivative, so that means that the derivative changes signs around it. All right.
Yep.
So what we could do is we could use my step-by-step process to split this function into sections where the derivative is either purely positive or purely negative. All right.
Yep.
So we identify points where the derivative changes sign. All right. And these are the only points where a derivative will change signs. The derivative can only change signs at a critical point. You agree with that?
Yes.
Cool. So if we find the critical points, find out which ones have a sign change, we can figure out all of the intervals where the derivative will be positive or negative. So I know that on this side, the derivative will always be positive. In this interval in the middle, it is always negative. And in this interval over here, it's always positive, going this way.
Yeah.
And all I did to do that was I identified the critical points, figured out whether there was a sign change, and I realized, sign changes can only occur at critical points. So the regions in between two critical points have to have the same derivative, have to have the same sign derivative everywhere. Okay. Any questions on that?
All good.
So what I need you to find with is, hypothetically, if I gave you this function, I said split it up into intervals of positive and negative derivatives, you would just find the critical points, identify whether there's a sign change, And if there is, then you know how to label each side of the point, right?
Yep.
If there's a sign change here, then all the points on this side will be positive, and all the points on this side will be negative.
Yeah.
There's a sign change here, though, so all the points on this side will be negative, and all the points on this side will be positive. So using that, we know, well, in this region, it's going to be negative. In this region onwards, it's going to be positive, and in this region onwards, it's going to be positive as well. So I just need you comfortable with the idea of, hypothetically, if I were to give you a function, being able to split it into its intervals where the derivative is the same sign.
Yeah, definitely. I can do that.
Cool. And also note that just because there's two critical points doesn't mean that there's going to be a sign change.
Uh-huh.
All right. Square root of x, or not square root of x. X cubed, for example, has a critical point here, but the derivative is always positive.
Yeah.
Cool. Except for this point, the derivative is always positive. So just because a critical point exists does not mean that there's going to be, you can split it up into intervals here.
Yeah.
Because you still have to use the first derivative test to make sure there's a sign change.
Yep.
All right. Good on that?
Yes.
Cool. All right. That's slide done. All right. Concavity. Visual representation of the second derivative. Let's go into Jamboard. All right. So we've been talking about the second derivative a lot. All right. And I said eventually we would come back to understand what it means in the context of the first function, right? Because the first derivative, we can see super easily how that plays into the first function, right? It just represents the slope of the first function.
Mm-hmm.
So so we can see how the derivative function manifests itself in the original function, right? Is the slope of the original function.
Mm-hmm.
But if I asked you, what is the visual representation of the second derivative in the original function, you'd probably be like, I don't know, right?
Yeah.
But it does exist, and I'm going to try and poke at it and see if we can get it out, all right?
Okay.
All right, cool. I'm going to draw a function like this, all right? What do you notice about the slope around this point? It's changing very quickly, right?
Yeah.
All right? It's decreasing very quickly. The slope is decreasing very quickly.
Yes.
So the rate of change of the slope is very negative, which means the second derivative is very negative because that's the second derivative is the rate of change of the slope.
Okay, yeah.
Right? So also, if I went like this, right, the slope is changing very slowly.
Yeah.
It's decreasing, but it's changing very slowly. So so the second derivative would be slightly negative. Right. So when the second derivative is very large and negative, we get our function looking very curvy. When it's only slightly negative, we get our function looking not so curvy. Because the second derivative tells us how quickly our slope is changing. A high second derivative in the negative direction means our slope decreases very quickly, so we get a kind of drastic curvature. If it's only slightly negative, then we're going to get very minor curvature because the slope is not changing very quickly. So with this, do you see how the second derivative represents how curvy the original function is?
Yes.
Cool. So if I had a function look like this, all right, you could tell me that here the second derivative is large and negative.
Yeah. Very negative. Yeah.
Here it's not as large as here, but it's large and negative here.
Mm-hmm.
It's large and positive here.
Yep.
Etc. Stuff like that. So do you see how this second derivative manifests itself in the original function as its curviness?
Yes.
All right, cool. So if we had a line like y equals x, right, what can you tell me about its second derivative? It's always 0, right?
Yeah, so it's because it's not, the slope isn't changing.
Exactly. So, and you notice that the line is not curvy whatsoever.
Yeah.
All right, cool. And the parabola y equals x squared has a constant second derivative. All right.
Yeah, because that's not changing.
Yeah, because it's the same curviness everywhere, right? It curves up the same way. All right, cool. And if a function had a second derivative that was another function, right? That just means that the curviness depends on where you are, right? Mm-hmm. For example, like this has a derivative function that depends on x, right? The slope depends on what your x value is.
Yeah.
If the second derivative depended on x, that just means the curviness of the function depends on where you are.
Mm-hmm.
Pretty. I don't think that's too groundbreaking, but correct me if I'm wrong.
Yeah.
Cool. Okay. So, are we fine with the idea of second derivative representing a function's curviness?
Yes.
So now, if you look at a function, you can see, we could see the first derivative of a function by looking at its slope. We could see it manifest itself in the original function.
Yes.
Now we can see the second derivative manifest itself in the original function through its curviness.
Yes.
All right, cool. Awesome. All right, I'll read this slide, and I think it's what I covered, but if there's any other points, I'll reiterate that. We can clearly see how the first derivative relates to the graph of the original function. It tells us the slope of the original function at each x-coordinate. But how can we see the second derivative of the original function in its graph? The answer is the second derivative tells us how curvy the original function is at that point, which is what we just discussed. And the reasons for that is what I described. The second derivative tells us how quickly the slope is changing. So if the slope is changing very quickly, the more curvy the function will be.
Yeah.
Cool. The slower the slope is changing, the less curvy the function will be. The second derivative of a function tells us how quickly the slope changes by definition. So in relation to the original function, the second derivative tells us how curvy the function will look. Pretty much what we talked about.
Okay.
So concavity provides a way to describe what the second derivative is like around a point. All right, and we use two terms, and I'm going to explain it in this slide. All right, so when the second derivative is positive, our slope is going to increase. So if we had a function that looked like this around this point, would you agree the second derivative is positive because the slope is increasing?
Yes.
All right, cool. So we call this shape concave up because you can see it's kind of curving upwards, right?
Okay, yeah.
Cool. And when a function is concave up, that means that the second derivative is positive from what we outlined.
Yep.
Cool?
Yes.
Cool. Similarly, if I had a shape that looked like this, what can you tell me about the second derivative in this region?
It is going down.
So if the slope is decreasing, what does that mean about what is the sign of the second derivative?
It's negative.
Exactly. So this shape is called concave down because it's kind of curving. You see it's curving downwards.
Yeah.
All right. And when a function is concave down, then our second derivative is negative. All right. We good on that?
Yeah.
Cool. Let's look at x squared. We know x squared has a second derivative of 2. It's always positive. And you see the graph is always concave up, right? It's always curving upwards.
Yeah.
Even on this side, it's getting close. It's curving upwards, right? It's getting more and more positive. Because it's getting less negative. I mean, it's really negative over here, and it gets less negative.
Yeah.
So it's always curving upwards. So you see how this entire graph is concave up.
Yes.
So even if we had no idea that the second derivative was a positive number, just by looking at this graph and realizing it's concave up everywhere, then we know that the second derivative is positive just from looking at that one observable fact about the graph.
Yes. Yes.
So that's why it's cool, because we can from learning, if we know the shape of the graph, we already get information about the second derivative there.
Mm-hmm.
Cool. Any questions?
All good.
Awesome. You're killing it, by the way.
You too.
Thank you. It means a lot. All right. All right. Concavity provides a way to describe the second derivative around a point. I described this. A function is concave up on an open interval, just like an interval between 2 points, if the derivative is always increasing there, or if the second derivative is always positive. That's what we talked about. This will make the graph curve upwards. A function is concave down on an open interval between 2 points if the derivative is always decreasing there, or the second derivative is always negative. This will make the graph curve downwards. So here's 2 sections of a function, and you can see here the graph is concave down, and here the graph is concave up. We cool on that?
Yes.
And we're going to get into something in a second. Notice how here the concavity changes.
Yes.
At this point, we go from concave down to concave up. This is a change in concavity.
Yep.
We call this a point of inflection, and we're going to talk about that in just a second.
Okay.
And I will say the idea of inflection points came up in the BC Calculus exam FRQ. So I'm not just teaching you useless information. This is some important stuff, I guess.
Yeah.
All right, cool. So that's a sneak peek into the next thing we're going to talk about. Notice how here the concavity changes.
Yes.
So we call these points inflection points. Any questions before I move on?
I'm all good.
Cool. Points of inflection. A point of inflection is a location where concavity changes. This can only happen when the second derivative is 0, and I'll explain that with a very quick example. All right, so the second derivative, y double prime, is the derivative of the first derivative. That's a mouthful, but you get what I'm saying?
Yes.
Okay, cool. All right, and remember the intermediate value property for derivatives, right?
Yep.
That means that a derivative, let's say y double prime is at -2 here, and up here it's at 2, right? The intermediate value theorem for derivatives tells us we can't get from -2 to 2 without taking on every single derivative in between. So if there's going to be a sign change from a negative second derivative to a positive second derivative, right? That's where concavity is going to change because we go from a negative to a positive second derivative, right?
Yep.
The point of inflection has to occur when the second derivative is 0. Because of this intermediate value property, you can't get from a negative number to a positive number without going through every number in between. So it has to go through 0, and that's where the point of inflection will occur.
That makes perfect sense.
So yet again, I hope I'm also illustrating that these useless theorems we learn can actually be pretty insightful and useful sometimes.
Yeah, and like referring back to them can just like skip the step of explaining the idea and just be like, it's the same idea as this.
Yep.
Yeah, no, that makes perfect sense.
All right. So this can only happen when the second derivative is 0 or undefined. All right.
Yeah.
And as for the undefined thing, it's the same kind of logic for why maxima can occur at 0 or undefined, right? Maxima occur when the first derivative changes from negative to positive, right?
Yeah.
So that occurs when the first derivative is 0 or undefined. So if concavity changes when the second derivative changes from negative to positive, that can only occur when the second derivative is 0 or undefined. It's the same logic as the first derivative thing we did earlier. I hope that's not too confusing.
No, that makes sense.
Okay. All right. So this will only happen when the second derivative is 0 or undefined and has different values on either side. Remember, it's not like, who cares if, and I'll say this again, who cares if the second derivative is 0, but it's the same value on either side? All right. For example, let's look at x to the 4th. Would you agree it's concave up always? It's always curving upwards, this graph.
Yes.
All right. But at x equals 0, we could find the second derivative, right? The first derivative is 4x cubed. And the second derivative is 12x squared. You follow me on that?
Yep.
Do you see how the second derivative is 0 at x equals 0?
Yes.
But yet again, there's no point of inflection in the original function. So it's not enough for us to just say, well, the second derivative is 0, so therefore there must be a point of inflection. We have to consider what the second derivative is like on either side. Because if it's the same side on either side, then there's going to be no concavity change.
Yeah.
Okay. Any questions on that?
No, I think that makes sense.
Cool. Yeah. So as a backtrack, remember, a negative second derivative means it curves, it's concave down, it curves downwards. And a positive second derivative means it curves upwards. So if you want to change concavity, you have to change signs.
Yes.
So you can't, even if the second derivative is 0, if it goes from positive to positive again, there's no sign change, so who cares?
Yeah.
Okay. Cool. All right. Point of inflection is where concavity changes, yet again. Okay. Notation. If we can find the second derivative of a function, we sometimes say the function is twice differentiable. So if I gave you a function and said, this function is twice differentiable, that just means you can find its second derivative.
Okay.
You can differentiate it 2 times.
Yeah.
Does that make sense?
Yes.
Okay. At a point of inflection, the first derivative will have a maximum or a minimum. All right, and I'll explain that in a second. Right? We said that at a point of inflection, the second derivative is 0. All right?
Yep.
And the second derivative is the derivative, I hate this mouthful, is the derivative of the first derivative, right?
Uh-huh.
So if we drew our derivative function, let's say this represents our derivative, then the slope of our derivative function represents the second derivative.
Yeah.
So yet again, when our second derivative is 0, that's where we have our maximum or minimum.
Okay.
Of our derivative function, at least.
Yeah.
Cool. This is not the original function. This is the derivative function. All right. And the locations where the locations where the hold on, let me go back to the slideshow and see what it's saying. And the locations where an inflection occurs, the first derivative will have a maximum, right? Because you'll notice the slope represents the second derivative. It goes from positive to negative here. So there's a sign change.
Yep.
Here it goes from negative to positive. There's a sign change. Negative to positive to negative. There's a sign change, etc. So the maxima and minima of the derivative function represent points of inflection. Does that make sense?
Uh-huh.
If I gave you the derivative function as a graph, you could tell me where all the points of inflection are going to be by just looking at where the maximum or minimum occur. Because that's where the second derivative changes sign. Because the second derivative is the slope of the derivative.
Yes.
Okay. We cool with that?
Yeah.
So, and yet again, we know how to find maxima and minima of a function from what we just did.
Uh-huh.
So if we know what the derivative function is, we can just figure out where the maxima or minima are going to be from our process from before and figure out where the points of inflection are.
Yeah.
So finding points of inflection are not different from the process we did before. It's basically just doing the same process, but instead of using the original function, we use the derivative function.
Okay.
Any questions on that?
No, that makes sense.
Cool. Awesome. I'm super glad. Yeah. Yet again, the caution point I laid out still holds. Just because the second derivative is 0 does not mean that there will be a point of inflection. And we considered x equals 0 for x to the fourth. There has to be a sign change. That goes back to what I said about if there's a point of inflection, the first derivative will have a maximum. Because if the first derivative has a maximum, that means the slope of the derivative, or the second derivative, will change signs around that point.
Okay.
So the second derivative has to change signs for it to be a point of inflection. Okay. So this means to test for points of inflection, we have to consider the values of the second derivative around the point of interest and confirm a sign change. All right. Any questions on all that?
I think I'm all good.
Cool. All right. Is there anything that's confusing? Anything that needs clarification, or do you feel is it just a lot?
It's just a lot, but I mean, I think it all is pretty intuitive.
Good. So yet again, we can always review this, whatever. I may have bitten off more than I can chew, but most of these ideas are intuitive, I hope. So as long as you have them in your notes, we'll review them. All right.
Cool.
Second derivative test for local extrema. All right. I'll ask you a question. Here's a function. All right. Here's a maximum. Right? And here the first derivative is 0.
Yeah.
What can you tell me about the second derivative here, around this point?
It is negative.
Exactly. Here's a minimum. The first derivative is 0. What can you tell me about the second derivative around this point?
It is positive.
Exactly. So hopefully you can see where this is going. The second derivative test for local extrema is one that's a little easier because you just differentiate the function twice. If the first derivative at a point is 0 and the second derivative is negative, then we have a maximum.
Yep.
Like I said, like we just outlined. If the first derivative is 0 and the second derivative is positive, then there's a minimum.
Okay.
So that's the second derivative test. So now you have two methods to determine where extrema occur. And if one isn't working for you, you just use the other, right?
Yeah.
So we're just adding to our mathematical tool set. I love saying that. All right. Any questions?
Nope.
Cool. All right. Learning about functions from derivatives. With the tools we learned today, by looking at the graph of a function's derivative and second derivative, we can get a feel for what the original function looks like. This is because the first and second derivative tell us information about the original function and its graph, right? The second derivative tells us information about the function's curviness, and the first derivative tells us information about the function's slope. So if I put my hand over the graph of y, the first function, and just showed you the first derivative and second derivative function, you can already get a feel for what it's going to look like. All right. Well, first of all, you know, when x is less than 0, it's going to be concave down because the second derivative is negative. And if we go to our original function, that's exactly what we see. We see there's a sign change at x equals 0. So we would expect a point of inflection in our original function.
Yeah.
And do we get that?
Yeah.
Yes, we do. Okay, cool. So if we look at our first derivative function, we notice that from this point to this point, the slope is negative. So we should expect the slope of our original function to be negative between these 2 points. Is our slope negative between these 2 points?
It is.
Cool. And also, we see that our derivative changes signs here and changes signs here. So we should expect an extrema at those points.
Yeah.
Do we see that?
We do.
Cool. So all of this is just trying to emphasize that you can already extrapolate information about the original function just by looking at the graph of its derivative and second derivative.
Yeah.
Because they tell you information about the original graph. Is that cool?
Yeah, that makes sense.
Cool. Awesome. All right. Discontinuous derivative, continuous function. This is very straightforward. The textbook goes through depth to explain it. But let me graph the absolute value of x. All right. And its derivative is this. All right. And you can see why this is a derivative. On the left side, right, its slope is -1. On the right side, its slope is +1, right?
Yeah.
So the derivative function is discontinuous. Would you agree there's a discontinuity here?
Yes.
But the original function is continuous.
Yeah.
So it's possible to have a derivative function be discontinuous and the original function be continuous.
Yeah.
That's the only point it's trying to make.
Okay, word.
Cool. Good on that?
Yeah.
All right. Okay, we just finished like 4/5 of today's lesson. The next part is modeling and optimization, but it's very, very light and very straightforward. All right.
Okay.
So I think now might be a good stopping point. I'm going to stop the YouTube video and I'll talk to you individually, Henry, in just a second. All right. So next video is going to talk about modeling and optimization. I hope to see you there. I'll see you guys in the next video.